Okay, so the title of my talk is Superconductivity Following a Quantum Quench, and there will be two parts to this talk. So for both the parts, I'll consider a situation where initially I have a system of free electrons in thermal equilibrium at some temperature T. The initial state will be that of a normal phase. And then we will study the dynamics, unitary time evolution, under the sudden switch on of attractive interactions. And so in part one, I'll consider the case where the dynamics is still such that one stays in the normal phase, but one is arbitrarily close to the critical point, meaning that even though you are in the normal phase, superconducting fluctuations are extremely important. The scattering off of electrons of these superconducting fluctuations would matter a big deal. And so the goal of this part of the project would be to make some predictions for how the electron spectral density evolves in time after the quench. And then maybe hopefully somebody will do time-resolved RPS and be able to see it. Then the second part of the talk is, again, I'll start with an initial state of normal electrons, but I will now quench deep into the superconducting phase. Now, we were hearing all morning that there's a lot of interest in competing phases and maybe able to stabilize one phase relative to another out of equilibrium. And usually, people are talking of very different kinds of phases like charge density waves and spin density waves and superconductivity. I want to ask a much simpler question. I'll only look at the possibility of being in a superconducting phase, but I'll look at a simple case where you have several different superconducting orders. So that's, of course, always possible. A lattice has some underlying crystal symmetries, and due to that, there are inherently S-wave order parameter that can be allowed, D-wave, F-wave, etc. And so the question I'll ask is that maybe in thermal equilibrium, the system prefers one kind of superconducting order parameter. Is it possible to tune the quench amplitude in such a way that the non-equilibrium steady state actually wants to go into another kind of superconducting order? So I'll look at the question of competing phases, but competing superconducting phases. So those are going to be the two parts of the talk. And feel free to stop and ask questions. Okay, so part one. So this is the one that I call critical quenches. My initial Hamiltonian is just that of free electrons. So K is the electron momentum, sigma equal to up and down are the electron spin, and alpha is some orbital index which I'll allow to take n different values. There is a technical reason for using the orbital index because I'll be trying to do some systematic diagrammatic theory for this time evolving system, and 1 over n will be my small parameter. And so, so remember that this n is an orbital index. But the superconductivity will be the usual singlet superconductivity involving up and down, k up and minus k down spins. So initially, I just have free electrons corresponding to the ground state of this Hamiltonian, and let's say that there's even a temperature T. And now I suddenly switch on this pairing interaction, which is a quartic interaction written as follows, where delta is C up, C down, and again, alpha, note that this alpha index takes values up, n different values. Now, obviously, there is a long history of studying quench dynamics in a superconductor, but just to put things in context, what is going to be different in what we are doing? Well, I mean, so there's been a lot of work, for example, Levitov's work, which got discussed a little bit, that Emil Yuzbashian and Boris Altshuler. They were all studying quenches within the superconducting phase, and in that case, average value of this quantity delta is really non-zero, and then they were studying dynamics in the mean field limit. So average delta is 0, so for that reason, even the mean field dynamics is interesting and non-trivial. For us, at the mean field level, nothing interesting happens, because for us, average delta is 0. So we have to go and look at effects beyond mean field accounting for fluctuations. So how do we do that? So this is where the 1 over n expansion becomes extremely important. So we will use a two-particle irreducible formalism. This is a very standard formalism where you write the effective action for the system in terms of a two-particle Green's function. So the solid line here is the electron Green's function. The dashed line here, it represents the attractive interaction, the pairing interaction. And this is how the action looks to order 1 over n. So basically, the advantage of keeping these set of diagrams is that it's taking into account all powers in U, And yet it's like, the control parameter here is really this number of orbital degrees of freedom. And often this is a very powerful method to use when you are interested in physics close to the critical point, which is going to be what we'll be interested in. So if I just want to do some power counting, the dashed line here comes with a power of 1 over n. And then every time I have a closed loop, I'm summing over all these orbital indices. And so that gives me a factor of n. So this diagram is of order 1. And you can see that all these diagrams by this way of counting are of order 1. So you have to keep this infinite series. Now, once you agree that this is going to be my action, then everything else follows from that. And this is really how one should always remember to make conserving approximations when studying dynamics. Yes?
I'm more used to superconducting conserving approximation here in this kind of ladder. Is it the same?
It is the same thing if I rotate it around. Yeah. OK. So now, so once I have this 2pi action, the self-energy just comes from taking the differentiation of this 2pi action with respect to the Green's function. And this is what the self-energy looks like. A solid line corresponds to the electron Green's function. And this double line here actually represents a string of bubbles.
Can I ask, when n is large, is the model integrable or not? In the infinite range?
Well, I mean, no, it's not. Yes, it's not. Yeah, it thermalizes. Yes, absolutely. I mean, there still may be, OK, so I know exactly how it works for the bosonic theory. What happens is that there are still many conserved quantities, but strictly speaking, classically, OK, so this problem, I take that back. Yes, this is going to thermalize.
I know in some systems these approximations are kind of deceptive, so
right.
I send them to infinity, but because the model effectively integrates,
yeah, I hear you.
Is faster than n.
So in this case, it's going to be integral. Yes, it will thermalize. But again, I'm not going to really look at the issue of time scales to thermalization. I'm going to be more interested in the transient regime. But yeah, that's a good question. So now, so obviously this is not a very easy problem because you have to solve for this electron Green's function self-consistently. And this Green's function corresponds to determining the self-energy, which is this product of the Green's function again, and this whole series of loops where the full electron Green's function is entering. So it's a difficult problem to solve. So what are we going to do? So the first thing we will do is a very crude approximation. It's a perturbative calculation, just to see what kind of answer we are going to get. And that's why I call it like the short time expansion. At short times, you expect some kind of perturbation theory to be valid. So we'll first do that and make some predictions for how the electron spectral density evolves in time. And needless to say, you'll find at some stage that your perturbation theory breaks down very badly. But what's nice about it is that it's a diverging result which has physics in it. There's a very good reason why that spectral density that I'll give you results for is going to keep growing and growing in time. And it's not going to be an unphysical divergence. And then we'll take that into account by actually solving the problem self-consistently. So earlier I had thought that this was not possible, but actually it turns out one can do it.
You're quenching from where to where, from Fermi gas to what?
To very close to the critical point. But still in the, yeah. So the average delta is always 0. So this is all just electron Green's, C dagger C Green's function.
But that's the critical point. So if you have any negative interaction, you always, at zero temperature, always go.
Yeah, so what I mean by critical point is that when I want to, I'll expand it on in a little while. But when you look at the dynamics of this Cooper-on, so this Cooper, then it's when the dynamics looks gapless.
But if you look at the equilibrium Hamiltonian, so the Hamiltonian is quench too.
Yeah, you have to tune the parameters of the initial as well as final Hamiltonian in such a way that indeed the dynamics at long times is critical.
So when you start from the 0 temperature?
No, initially I take care to be at a non-zero temperature for the fermions. But it's still a closed system. So yeah, I mean, there are technical difficulties of having to start with a zero temperature Fermi gas, which I don't want to go to. Because I want to be careful and I want to be near the classical critical point. But you'll come to the, I'll explain what I mean by critical quench a little carefully. But the thing is that you do have to tune the microscopic parameters of both the Hamiltonians to ensure that at long times you have some kind of power law decay in your Cooper-on.
Long times, but still without accounting for thermalization. just
Yeah, exactly.
thermal.
Yes, that's true, without accounting, yeah. So, for people who, so this string of bubbles here, represented by the dashed line, is what people often call the Couperon. So often it makes sense to think of this problem as a coupled electron boson problem, where the bosonic part is this Couperon propagator that I'm going to call D. So let's do your short time analysis. The short time perturbative analysis is that wherever I have this solid line corresponding to the electron propagator, I'm not going to put in the self-consistent value. I'll just put in the bare value, just the free Fermi gas. And so if I do this treatment, what do I get? So the polarization bubbles, the retarded and Keldysh polarization bubbles will look familiar to many of you who are used to doing these kind of calculations. These two are just related to each other by fluctuation dissipation theorem, because the initial electron gas is at thermal equilibrium at some temperature T. And now the Couperons, you can write down the Couperon, look at the equation of motion for the Couperon, is just U inverse minus this polarization bubble, and it shows overdamped dynamics. So this is model A. Again, should be familiar to many of you. Maybe it got even mentioned a couple of times today. So at this level, the retarded propagator doesn't know anything about the quench. It is still time translationally invariant. When you look at the polarization bubble, it depends on the momentum of the Couperon, and it depends on this constant value. And so you have to tune the R, right, so that you're at the critical point. So this is what I mean by doing a critical quench. That this R that is sitting here, which is controlling the decay of the Couperon, is going as Q square.
And I'm still in the level of the Hamiltonian, so whenever you have negative interactions, it's a superconductor, right?
So I'm not going to, no, not necessarily, it depends on the temperature.
Oh, well, okay.
So I'm always, yeah. So that is why I always start with a system at finite temperature.
But then also you have the temperature before the quench and after the quench. Sometimes you're pumping energy into the system once you quench, right? So you kind of know that, so which one is the...
So for the transient regime, okay, so I'm not interested in the absolute long time regime where the system is thermalized. So I'm happy with just the initial temperature of the electron gas. Yeah, yes. Okay, so now the other the quantity that knows about the quench is the Keldysh propagator, D propagator. You can see that it is no longer time translationally invariant. It depends on both the time difference as well as the mean time. And this behavior is consistent with one where the quench occurred at t equal to 0. So in all my expressions that I'm writing here, the quench took place at t equal to 0. So with this, so one thing of course to notice is that if I'm really at the critical point where r is equal to 0, then this Keldysh component of the Couperon shows scaling, where the scaling form is temperature times the time after the quench and some nice scaling function. And what the scaling function is saying is that if you're at the critical point, there are only two scales in the problem. One is the time after the quench, and one is a length scale associated with the time of the quench, which goes as square root of t because the dynamics is diffusive, right? So the Couperons, they're effectively coupled to this finite temperature reservoir, and its dynamics is diffusive, and for that reason, the position and time dependence are related as follows: x goes as square root of t. Okay. So now if I plug in these results for the Keldysh component of the Couperon and the bare electron propagator, you can determine what the spectral density is. And you might ask, well, how do I even define the spectral density? The system is kind of time evolving. There are two different times. So we go into Wigner coordinates. And it makes sense to go into Wigner coordinates because there's a separation of time scales in the problem, coming from the fact that the Couperons, the Cooper pair fluctuations, are changing very, very slowly in time as compared to the inverse temperature. And so you can truncate the Wigner, when you go into Wigner coordinates, you can just keep the leading order term in the Wigner expansion. And then with this, you can, after taking the imaginary part, you can look at what the spectral density is doing. Tau inverse is the lifetime of the electrons, and it obeys a scaling function as the energy square of the electrons time after the quench divided by the temperature. And so here is the results for the spectral density in this crude perturbation theory result. So the top box is for dimension d equal to 2, and the bottom box is for dimension d equal to 3. What you find is that if the energy of the particles, electrons, okay, so here I'm measuring all the energies with respect to the Fermi surface, Fermi energy. So when the energy of the electron is large as compared to 1 over the time after the quench, then this lifetime kind of saturates to a value which goes as 1 over epsilon in d equal to 2 and log of epsilon over t at d equal to 3. So if I look at the large energy behavior of the electrons, the spectral density, which was initially 0 because I started with 3 fermions, well, saturates to a value which is kind of okay. At this level, you don't see that there's anything wrong with perturbation theory. The problem with perturbation theory comes when you start looking at the lifetime of the electrons which are right at the Fermi surface. You find that at d equal to 2, its lifetime grows unbounded with time as square root of t for d equal to 2 and as log of t at d equal to 3. So this should not again be surprising because like I was warning you all along, I was doing a very crude approximation for the spectral density. I didn't do it self-consistently, I just put in the bare electron Green's function to find out what the lifetime was doing. But the fact that it is actually a lifetime of the fermions at the Fermi energy, which is growing unbounded, has a very nice physical explanation, which is given by this cartoon. So essentially what's happening is that you have all these puddles of Cooper pair fluctuations all over the place. And the reason why this lifetime is arising is because an electron is coming and they're reflecting into a hole. Now, when the electron energy is very far from the Fermi energy, these processes are highly off-resonant, and so you can do some crude perturbation theory, it's fine. But when you're right at the Fermi energy, this Andreev reflection process is resonant, it's on shell. And so this naive calculation that I did, which is equivalent to doing Fermi-Golden's rule, is no longer valid. So for the electrons at the Fermi energy, one has to take a little bit of care, and that is why we have to do something better and do these problems self-consistently. So what did we do? Well, first thing we did is that we noted that because the dynamics of the Cooperon is model A, well, the dynamics of model A under quench is been studied a lot 20 years ago. So we used the results from that literature, which is studying the full dynamics of the propagator. Now, the previous result I told you, this one was completely quadratic in the, this was just a constant, but now it has to be self-consistently determined because of the interactions between the bosons. And as long as, again, if you do quenches to the critical point, the details of how you solve the model A dynamics is not so important. The standard techniques available are either you can do RG or you can do Hartree-Fock, and both of them give you good, the right scaling forms for the Cooperon. So here is the references to papers that had discussed quench dynamics in model A. So the phi that's entering here, this is your typical model A coupled to a reservoir which is at some temperature T. And this, for us, this temperature is coming from the underlying Fermi gas to which the Cooperons are coupled to. And the way you should think of this phi is that it's the Hubbard-Stratinovich field which is used to decouple the original interactions. Okay? So if you pick up these model A results, then you have scaling forms for the Cooperon that look something like this. So there are 2 times here. So let's say the quench took place at time 0. You have 2 times here denoted by S and T. And so at short times after the quench, because I've done a critical quench, again, remember that there is no scale in the problem other than the time after the quench itself. And so what happens is that this lack of energy, any energy scale in the problem ends up giving you aging dynamics like the one shown here. The results are not time translationally invariant, and they depend on the ratio of the 2 time indices with some universal exponent theta, and then some scaling function. And then at very long times, eventually the Cooperon correlation functions reach thermal equilibrium because the underlying reservoir to which it's coupled is at finite temperature. But we are not interested in the very long time thermal behavior. That's not interesting. We're interested in the transient regime because, like I said, we are motivated by all these experiments using pump probe, where you can create these transient regimes and have a Cooperon which is showing this kind of aging dynamics. And so then the question is that if my Cooperon is really behaving like this, what does it imply for the spectral density? So what we did next was that we took the full scaling function for the Cooperons using model A machinery, which takes a form like this. And then we actually solve the self-consistent solve for the spectral density self-consistently. And so this is again something that one could do only because the person who I was working with, Yona, is very smart, and he'd figured out how to solve it self-consistently. And so these are the results for the self-consistent expressions for the spectral density following a quench. So on the left-hand side is the result for d equal to 3. Sorry, for the right-hand side is the result for d equal to 3. On the x-axis is the energy of the electron divided by the temperature, and on the y-axis you have the lifetime. So in both these plots, basically these different lines at different times after the quench. So obviously for both these plots, the shortest time is almost hugging the x-axis because the lifetime is 0, and then the lifetime begins to increase in some way. Sorry, the inverse scattering time. Or spectral density begins to increase in some way for both cases. For d equal to 3, this saturates. Okay? So when you did just bare bones perturbation theory, it kept growing as as log of t. In the self-consistent way of doing things, you cure this divergence, and the spectral density saturates. Moreover, it's interesting to note that if you look at the tails of this function, which means that you look at the spectral density at large energies, you recover the results from perturbation theory, which is what you expect. For electrons that are very far from the Fermi energy, the scattering process is highly off-resonant, so you don't have to do any fancy self-consistent theory, and the simple Fermi golden rule perturbative calculation that we did works very well. This is for the tails. But for the lifetime of the electrons right at the Fermi energy, you need to do it self-consistently to get this steady state result for the spectral density. And this is a plot of how the spectral density evolves in time in d equal to 3 for the fermions at the Fermi energy. So initially, it increases as log of t as perturbation theory predicted, and then it saturates in some way. For d equal to 2, on the other hand, the problem is that the results does not saturate. While the perturbation theory results showed a divergence which went to square root of t, in this case, it's not as bad as square root of t, but it's still there. It goes as log of t. And the reason that happens is that at d equal to 2 for our problem, there is no true critical point. It's a lower critical dimension for this problem. So we don't expect to get a self-consistent answer out in d equal to 2. Yet this is just a way to check what's going on. But d equal to 3, we get a nice self-consistent result. And so what's going on right now is that we are now looking into using this two-particle irreducible formalism to make predictions about the optical conductivity. So for that, you have to solve the full kinetics, but we'll get to that later. Are there any questions for this part? Because then I can move to the next part quickly. Okay. Fine. So then let me go to part 2, which is not about critical quenches, but it is you start with a system of free electrons, but you quench deep into the ordered phase, and you try to ask the question, in principle, there are many different competing superconducting order parameters. Can you tune the preferred order parameter by tuning the quench amplitude? And so what was the system we studied? So we looked at graphene, and we looked at the Haldane model. So we were looking at a 2D system in an hexagonal lattice. One was graphene, and the other was a Haldane model, which you can think of as taking graphene and applying a circularly polarized laser to it. A very high frequency circularly polarized laser, so that you don't create, so that the mapping to the Haldane model is almost exact in the high frequency limit. So for all practical purposes, I will just model the initial Hamiltonian either as graphene or as the Haldane model, and ask what happens when you switch on a pairing interaction. Okay? So this interaction, it will be convenient to write the interaction in the TJ form. So there is no double occupancy of the sites, and just interactions between nearest neighbors through this kind of spin-spin term. And it turns out that if you write it this way, then the natural way to write the pairing interaction is in the following form. So the pairing interaction is between a singlet formed out of an electron sitting on sublattice A and sublattice B.
Good question. Haldane model is an insulator, right? Do you want to be an insulator and do superconductivity? Yeah.
So we are going to have to dope the system a little bit. We are not at half filling.
You want Haldane model anyways. If you Haldane model is interesting because it's a logical insulator.
Yeah.
You don't want an insulator, you want to drive the superconducting state. You want the Fermi surface.
So the way we'll get the Fermi, okay, so the reason is a little bit historical because we were looking for topological superconductivity and things like that, yeah. Okay, and another good thing about the Haldane model is that if it's really coming from, so people had been thinking about getting superconductivity in graphene in equilibrium, right? I mean, there are all these papers, but the problem is that you can get fancy D-wave phase, but you have to dope it very, very deep. Now, if you take graphene and get Haldane model by shining light, then because of the bland flattening effect, you don't have to dope it to the same amount. So that's also an attractive reason for considering the bland flattened version of graphene. And on top of that, if it's circularly polarized, then you can try to look for topological superconductivity.
As far as quench physics is concerned, it doesn't really matter. Is it?
No, I think it matters because the thing is that it's important for us that you are on this lattice, which can allow for S-wave, D-wave, D plus ID, and D minus ID. I could not have got this physics in that very simple generic model I was talking about, where from the very beginning you throw away, all these different competing order parameters by saying, okay, let's just focus on S-wave. Yes, I'm almost done. So now the technical machinery here is much simpler. What we do is just mean field. So we just look at the dynamics of this order parameter under linear response. So this is the order parameter at time t, and pi is the response function at t prime, and delta is again the order parameter at time t prime. The important thing to note here is that because I'm on this lattice, which is hexagonal, this order parameter has it should be viewed as a 3-component vector, because the singlet formation is between A and B sublattices, and for every A sublattice there are 3 different B sublattices. So this delta can take 3 different values. And so when this delta is such that it takes the same 3 values along the 3 different directions, you have S-wave superconductor, which makes sense because the order parameter looks the same in all directions. But you can also have these 2 other phases. You can have D plus ID and you can have D minus ID. This is where you sit on the A sublattice and kind of go around in a circle, and the order parameter changes phase. In fact, it has a node, right, like you expect for a D-wave superconductor. And so D plus ID, you pick up one kind of phase going in the clockwise direction, and D minus ID is just a time reverse counterpart of it. So anyway, so this underlying C3 symmetry of graphene and Haldane model has this nice property that the S wave, D plus ID, and D minus ID are irreducible representations of the crystal symmetry. And when you think of this problem in equilibrium, what these people showed is that in equilibrium, after sufficient doping, it'll prefer D wave. Okay, so if you're in graphene, it'll prefer D wave. But the problem with graphene is D plus ID and D minus ID are degenerate. So then you have to use some extra energetic considerations, like D plus ID opens up a gap. And so the system would prefer to go into this time reversed, spontaneously go into this time reversed superconducting phase. What is nice is that if you start with the Haldane model coming from the circularly polarized laser, it already breaks time reversal. And so it lifts the degeneracy between D plus ID and D minus ID. Anyway, so to cut a long story short, what we did here is that, remember that in graphene and the Haldane model, if I just did the equilibrium phase diagram, the system prefers D wave, okay? But, so now we want to see that if you quench this system, what would be the dominant order parameter? So we just take some arbitrary random vector and time evolve it. So this is as a function of time. In this particular case, you can see this is the equilibrium result. D plus ID is growing faster than D minus ID, which is growing faster than S wave. So you would conclude from it that the system prefers D plus ID. And indeed, this is the equilibrium phase diagram. But it turns out that if I make the quench amplitude larger and larger, eventually the S wave grows faster than the D wave. So you can obtain a quench phase diagram as follows. On the x-axis, I have temperature of the initial Fermi gas. And on the y-axis, I have the quench amplitude. Initially, J was 0 and it's being quenched to some non-zero value. Now, when this quench amplitude is small, you recover the equilibrium phase diagram where out here you have a normal phase, then you go into a chiral D wave if you are in the Haldane model. But if you make the quench amplitude even larger, you eventually go to S wave. If you had just used equilibrium results, you would have concluded this whole phase was D wave. And the reason for this is that when you make the quench amplitude very large, you create highly excited quasi-particles. And that produces dephasing. And dephasing is bad for D wave, because D wave changes sign several times in the Brillouin zone. So on an average, it will just average out to 0 if all the quasi-particles in the Brillouin zone are active. And so really, if you make a very large quench, then you just kill it. Whereas if you make a tiny quench, then ultimately it's the fermions near the Fermi energy that will be dominating the growth of the other parameter, and you'll get back the equilibrium result of chiral D wave. So anyway, so with this I will conclude. So part 1, in both cases I showed you quenches from a normal phase. But in one case it was arbitrarily close to the critical point where we had gave some predictions for time evolution of the spectral density. And one ongoing work is looking at transport now. And then the second is a kind of mean field treatment, but it was trying to come up with a situation where by tuning the quench amplitude, you can stabilize a different superconducting order than what you would naively expect from equilibrium physics.